What we have here is sort of a spring gun that shoots steel balls out of the gun. Get out of there, and the steel ball goes into this little chamber. We have a plunger here. It cocks it back 3 clicks, and then it shoots the little steel ball into this pendulum. When I pull up on the trigger, what happens is it gets caught in the pendulum. The pendulum swings up. There's a little angle measuring device here on a protractor, and when the arm swings up, it moves the little arm up and it stays there. So we can actually measure the maximum angle that this swings out to, and we can use that information to calculate the speed of the steel ball coming out of the spring gun. So that's the basic goal of this lab today, is to find the speed of the bullet coming out of the spring gun. We're going to find it 2 ways. One way is by seeing how far it pulls the pendulum up, to what angle. And the other way is by shooting it on the floor, and by measuring the range, we can back calculate to the initial speed of the steel ball. So the goal today is to find the speed of the steel ball coming out of the spring gun 2 ways. The first way, using the pendulum. By the way, this is called a ballistic pendulum. The police forensics units use ballistics, in this case the ballistic pendulum, a much more sophisticated device than this, to measure the speed of bullets coming out of guns. So basically, the 2 principles that are involved here in this first method is the conservation of momentum and the conservation of mechanical energy. So here's our spring gun. Here's our steel ball. We're eventually going to measure the mass of that steel ball and call it little m. The steel ball is going to be trapped in the pendulum. The mass of the pendulum we're going to call capital M, or uppercase M. So the steel ball comes speeding out of the spring gun, gets caught in the pendulum, and makes the pendulum swing up to a certain angle. 2 things are happening here. First of all, we have a collision. It's a collision between the little steel ball and the pendulum. What is conserved during every collision, no matter whether it's bouncy or sticky, whether it's elastic or inelastic, the one thing that's always conserved in any collision is momentum. So the first part of the activity is a conservation of momentum, which means that the initial momentum is going to equal the final momentum of the collision. So what's the initial momentum of this process? Well, in the beginning, the mass has a velocity, the initial. By the way, that's the ultimate goal of what we're looking for in this lab. The pendulum has an initial velocity 0. So the total momentum of the system before the collision is going to be the mass of the ball times its initial velocity. The mass of the pendulum doesn't come in here because it isn't moving. The final momentum, as soon as the pendulum catches the ball, it's going to be moving with a final velocity. So what's the momentum of the pendulum and the little ball at that final velocity? It's going to be the total mass of the ball plus the pendulum times the final velocity. Our goal is to find the initial velocity of the ball, which is how fast it's coming out of the spring gun. So solving for VI, we have little m plus big M times final velocity divided by little m. How did we get this? Conservation of momentum. Why is the momentum conserved? Because it's a collision. For every collision, the total momentum of the system is conserved, giving us an expression for the initial velocity of the ball just as it comes out of the spring gun. Now we can measure little m and big M, not a problem. But what about the final velocity of the pendulum and the ball moving away together? How do we get that? We get that by the conservation of mechanical energy. We know that when gravity is the only force acting, then as an object swings up, mechanical energy is conserved, which is to say that the potential energy plus the kinetic energy equals the total mechanical energy of the system. That's conserved. So that means that the kinetic energy at the beginning, the potential energy is considered to be zero because it isn't raised up, and the total mechanical energy is 1/2 mv squared. Once it gets to its maximum height through a distance y, now it has potential energy, mgy, but no kinetic energy because it stops. It swings up and it stops. Now it's got potential energy and zero kinetic energy. This should be a plus sign, excuse me. 0 plus mgy plus 0 equals the same mechanical energy. So you can see here that at the bottom we have 0 potential plus kinetic energy. And then up here we have at the top potential energy plus 0 kinetic energy. Those two have to be the same because the kinetic energy is converted to potential energy. So the 1/2 mv squared at the beginning must equal mgy at the end. But let's be a little careful here. What is the m in this expression? It's the pendulum plus the ball together. So I'm going to come over here a little bit. 1/2 mv squared equals mgy. Well, what's the m? The m here is the ball plus the pendulum, and v squared. Now this is the VF, the final V in the collision that we were talking about before. Okay, that's got to equal the total mass that's raised up, which is also m plus big M gy. But a nice thing happens here, and that is that the masses cancel out because it's the same on both sides of the equation. So solving for V final, we get 2 times gy and take the square root. So if I can shoot the ball into the pendulum, raise it a distance y, I can immediately calculate the speed of the pendulum and ball together after the collision. But what's y? You know, it would be really hard if I had to measure y. Y is the change in altitude as it swings up. If I had to try to measure that, because it's going to swing back. But what I can do instead is use this angle to find y, the distance it swings up. So how do we do that? Let's take a close look at what's happening here. Okay, so we have the pendulum. And the pendulum has a certain center of mass that we're going to look at in a moment. Let's say the center of mass is right here, of the pendulum plus the ball. That's going to swing up. I'm going to make this bigger so you can see it better. Here's the center of mass. Here's the pivot point. It's going to swing up to some height, like this. Okay. Now, the height that it swings up to will be how far the center of mass rises. But what we're actually measuring is this angle here, theta. Now, we can make a nice little triangle here, where this side of the triangle is the radius of the circle this thing is swinging out. We're going to call that R, center of mass. It's just the distance from the pivot point to the center of mass of the pendulum. What we want is y. So also this side is also just the length of the pendulum. So if we could take the pendulum length and subtract this piece, we would get y. But what's this side of the triangle? Well, it's a right triangle. A squared plus b squared equals c squared. Or we can look at it as a cosine function. This side here is adjacent over hypotenuse. And so this side here is just r center of mass cosine theta. That's this piece here. So this piece is over the hypotenuse is the cosine. So this is just r cosine theta. So y then is just going to be the length of the pendulum minus r cosine theta. Now, the r's we can factor out. Now we have an expression for y that we can plug in here. So v final, which again is the pendulum plus the ball swinging up after the collision, it's just going to be the square root of 2 times g times r center of mass 1 minus cosine theta. All right, so, but what we really want is v initial. We have written here before, v initial equals the square root of 2gy. So we're just going to take this, oops. Oh, we already did that. Okay, that's fine. So what we had is the conservation of momentum was m v initial equals m plus m v final, and dividing both sides by m. So what we want to do is take this v final and plug it in here. Give us our final expression. V initial equals little m plus big M over little m times the square root of 2g r center of mass 1 minus cosine theta. Now it looks a little complicated, but it's exactly what you'll find on your data page. This is the expression that we just derived. It's a little confusing the way this is printed out. That square root goes over everything here. Just m plus m over m, square root of 2g r 1 minus cosine theta. So I just wanted to give you a feeling. I mean, I could just hand you this formula and say, we're going to measure these things, plug it in, and find the answer. But I wanted you to understand, and this is crucial, and I'm going to look for this in your lab report to see that you understand this, that this is the result of two things: conservation of momentum during a collision, conservation of energy during the swing up of the pendulum. The conservation of energy gave us this, and the conservation of momentum gave us this. Okay, so now that we have an idea of why it works, let's actually do it and see what we need to measure. By looking at our data page, you can see the first thing we need to do is find the masses of the pendulum and the ball. So, I'm going to remove the pendulum. There's a little axle here. Just going to pull that out, remove the pendulum, take the steel ball out. Let's do the steel ball first. Doesn't have to be exactly in the center for it to be a correct measurement. Come around to the front, get it. So it looks like we have 60, about 66.3 grams. So that's little m, the mass of the ball, 66.3 grams. You can say plus or minus, say, 0.1 gram. And now the mass of the pendulum. Okay, it looks pretty good. It's going to be 241.1. 241.1. That's going to be the mass of the pendulum. Grams, plus or minus 0.1 gram. Okay. Now a little bit trickier is measuring. Oh, you know what? I was supposed to take these weights out. It's okay. These things happen in a lab. Sometimes we have to measure things a couple of times. I've got to take these weights out because they're not going to be there when the pendulum actually swings up. We'll just take another quick measurement of that. Okay, looks like 142 exactly. So whenever you need to change the data point, the best practice is just cross out the old number, write the new one up above, 142.1. Okay, a little bit trickier is finding the length of the pendulum that's swinging up, the RCM. CM means center of mass. We're going to have to try to find the center of mass of this device. And it's a rather crude way of doing it, but it works pretty well. All we do is find the balancing point. Wherever it balances, that's going to be the center of mass. But that part has to have the ball inside because they're going to be swinging up together. Okay. I'm going to do it on this side because it's got a little bump over there. Okay, right about there. So what I'm going to do is mark that spot with a piece of tape. I'm going to grab my tape over here. It seems like a rather crude measurement, but it actually works pretty well. And that was balancing very close to the edge here. I'd say right about there. So that mark represents the center of mass of the whole system, the balancing point. So R, the radius of the swinging up of the pendulum, is going to be the distance from where it's pivoted, which is here, to R. So I need to measure the distance from the center of this hole, the pivot hole, to the center of mass. So I'm just going to lay the measuring stick here. And that looks like about 26.2 centimeters. So for RCM, I'm going to write 26.2 centimeters plus or minus 0.1 centimeter. Okay, now that we have our basic measurements taken, we can shoot the ball into the pendulum and see what happens. First, I need to replace the pendulum into its axle. There we go. Swings nicely. Now, I'm going to shoot it a few times just to see where it goes, so we can know where to place our angle indicator. There are 3 stops that are possible with this device. We want the strongest one, the third one. 1, 2, 3. Okay, so I'm going to slide the angle measuring device all the way down, pull the trigger, and it looks like it went up to about 68 degrees. We're just shooting it a few times, getting the feeling for it. About 68 degrees. Let's see if it's consistent. If we shoot it a couple of times. If we get the same result. About 64 degrees. Okay, that's not too bad. So the point is, there might be a little friction here. So instead of starting at 0 each time, I know it's probably going to go over 60. So I'm going to just start it down around 50. That saves all the friction of sliding down this area. So now we're ready to actually take measurement. So what we're going to do, shoot this thing 4 or 5 times, measure the angle theta, and record it on our data page. Okay, here we go. Number 1. And that looks like about 62.5 degrees. So I'm going to write that down right here. And these will be the numbers that you'll be using in your calculations. Let's shoot it another 3 times. We can get a good average. I'm pushing down on this so the recoil doesn't move the device. Okay, this time we've got about 66.0 degrees. So there is some variation. That's why we're going to take an average to try to eliminate some of that random error. A couple more times. Okay, looks like 65 exactly. One more time. Settle down a little bit. 65 again. All right, the fact that it's so consistent encourages me to have confidence in these numbers. So what you'll do is take these angles, add them up and divide by 4 to get the average. Then you can plug all these numbers into the formula that we derived. And that'll give you the speed of the ball coming out of the spring gun. Okay, so what we've just done is taken measurements to allow us to find the speed of the ball coming out of the gun, but we want to do it another way as well. What we're going to do this time to find the speed of the ball is we're going to shoot it onto the floor. Just going to shoot it straight horizontally onto the floor and see how far away it lands. So how does that work? Well, that's a matter of kinematics and two-dimensional motion, which we studied in chapter 3. So let's take a look. It's fairly simple, fairly straightforward. Here's the tabletop. Here's the floor. Here's our little spring gun. The steel ball shoots out with an initial velocity, which is what we're looking for, and lands on the floor a distance away from the starting point, which we're going to call capital R. Notice we're not talking anymore about the center of mass radius of the pendulum. We're talking about the range of the ball hitting the floor. And what we're going to need is the height that the ball falls through. Remember, the initial velocity of the ball is an x velocity, horizontal velocity, so it's a constant speed. It's just distance over time. It's the range of how far it goes divided the time it takes to fall this distance y. You probably remember from our study of kinematics, for falling objects, y equals 1/2 gt squared. So we can get the time from this formula, just t equals 2y over g, take the square root. So if we measure y, divide by g, we can get the time it takes to fall through that distance. Equal sign. Divide the range, which we're going to measure on the floor, by that time. And that gives us our final expression for the initial, which is the range over the square root of 2y over g. But it's a little bit nicer if I put this on the top of the fraction by taking the reciprocal. So that's equivalent to r times the square root of g over 2y. And that'll give us the speed of the ball coming out of the spring gun. And you'll find that formula in your lab handout on the last page, right here. Vy equals r square root of g over 2h, where the square root again is over everything there. So it's very straightforward measurement and calculation. But how do we actually measure these things? First of all, we need to measure the height that this is going to fall through. So to do that, this little white circle here represents the position of the ball inside the gun just as it begins to leave. So what do you think? What do we need to measure? The distance from the top of the ball to the floor, the middle of the ball to the floor, or the bottom of the ball to the floor? Well, which part of the ball is touching the floor? It's the bottom, right? So we're going to have to measure the distance from the bottom of the ball to the floor. Now here's a possible source of measurement error. This is a little tricky to measure because this white circle is over on the table, and it's hard for me to get the meter stick on it. So there's a source of possible measurement error. I'm going to try to counter that. It's kind of a crude method. Lots of error possible here. I'm going to line this ruler up with the bottom of the ball and just hold that, try to keep it level against the meter stick and read it off. It looks like about 80.5 centimeters. So H looks like, you can write this on your data page, capital H, the distance that it falls, 85.0 centimeters. Okay, so far so good. Now we need to shoot the ball on the floor and see how far away it hits. So we're going to have to measure the distance from the starting point on the floor to where it hits. So we need to mark out the spot on the floor which is directly beneath the ball. So I'm going to put a piece of tape down there and mark that off. Bill Nye the Science Guy never has these problems. Okay, matter of getting a piece of tape. Good enough. Okay, so what I'm going to do is try to put that directly beneath the ball. And I'm going to mark the spot. That'll be the starting point of our range. So the ball is going to shoot a distance from that spot to somewhere in the floor. Now, how do I know where the ball is hitting the floor? In order to do that, I need a way to mark it off. So what I'm going to do is shoot the ball on the floor and see about where it hits. Then I'm going to put some paper there and do it again, because when the ball hits the paper, it's going to make a little indentation that will indicate where it hit. Okay. It happens fast, so I have to kind of watch. Right down there somewhere is where the ball's going to hit. Looking at that spot, got my eyes on it. I think it was right about here. So I'm going to put that paper there and tack it down with a little bit of tape. Now let's try it again and see if the ball actually hits on that paper. Here we go. Okay, the paper was a little bit too close, so I'm going to reposition it right about here and try it again. Right, go. Good, okay. So, I don't know if you can see that in the camera, but there's a little indentation right here, which I'm going to circle with my pen. Let's do it a couple more times. Get a little cluster of spots. Hopefully they'll be not too far from each other. Never happened before. Okay. Here we go. It's not too far away. There it is right there. Let's do it one more time so we can get a little group. We can take the center of mass of that group. That one was a little farther away. There's some variability. Depends on how I pull the string and whether the device is moved or not. So I'm going to take the average position of these things somewhere in the middle, I say right about here. I'm going to measure the distance from the starting point on the floor to that position and call that the range. And if you're a 2-meter stick, put a 0 point at the starting mark. Looks like it just barely misses it. So that's 200 centimeters plus a little bit. Let's see how much that little bit is. Plus about 5 millimeters, half a centimeter. So 200 centimeters plus a half. So the range then is 200.5 centimeters. Now, with this data, you can plug that into your formula, calculate the speed of the bullet as it left the gun, and then you can get the percent difference between that velocity and the velocity that you calculated from the first equation of the pendulum. So in your lab report, you want to talk about the percent difference to see if it's close or not. Also, in your conclusion, I'd like you to talk about where was mechanical energy conserved during this lab and where was momentum conserved during this lab. It also asks you to calculate the percentage of kinetic energy that is lost during the collision of the ball with the pendulum. When the ball hits the pendulum, it loses some kinetic energy. I'm going to leave that as an extra credit problem for those of you who want to figure that out. Get another 10 points or so on your lab report by answering calculation number 3. Okay. So that there's no graphs to talk about in this lab, so we don't have to worry about that part of it. That's basically it for velocity of projectile. Good luck on your lab report.